There are 4 planets in the solar system on which you could actually stand. They are known as the Tellurian planets, rocky worlds born from the same cosmic dust disk. More than 4.6 billion years ago. But over time, each planet chose its own path. One burned like a furnace of eternal fire. Another froze into a realm of icy desolation. One became a world filled with ancient mysteries still left unsolved. And one alone nurtured life, yet now finds that life increasingly at risk. Beneath layers of cosmic dust and dense atmospheres lie secrets science has only begun to uncover. Water that once flowed across the surface of Mars. Acid storms swirling over Venus. Mercury, with nights colder than Antarctic and days hotter than flame. And Earth entering the danger threshold of its own making. And in this video, you will explore things no one has ever told you about these 4 rocky worlds. Proofs that challenge logi and hypotheses that may forever change the way we understand life in the universe. Born from the same swirling disk of dust and gas, these 4 worlds diverged along 4 distinct geological and climatic paths, shaped by uneven distributions of heat, water, atmosphere, and magnetic fields. Each planet is not a miniature version of the gas giants, but rather a natural experiment in the forces that determine planetary destiny. These differences began with a process scientists call the magma ocean and the first differentiation. In their infancy, all 4 planets were entirely covered by molten lava. This fiery crucible forged a 3-layer structure, a core, a mantle, and a crust. Beyond creating the internal structure, this process also triggered the redistribution of water and volatile compounds. This not only shaped the planetary surfaces, but profoundly influenced atmospheric formation. Water, when present, was trapped as ice or bound within minerals. Depending on each planet's distance from the Sun, its magnetic field, and temperature fluctuations. This explains why some planets, like Mercury and Mars, cannot sustain liquid water on their surfaces, while Earth provides ideal conditions for life. Meanwhile, Venus transformed into a hellish furnace due to a runaway greenhouse effect. Its surface was reshaped by global resurfacing events, leaving pancake-like domes and thousands of volcanoes in its wake. This differentiation did more than sculpt planetary structures and temperatures. It had major implications for the potential for life. Each Tellurian planet experienced a unique path of differentiation, resulting in dramatically different outcomes despite originating from the same primordial material. The central question remains, why did these planets evolve so differently, and could similar conditions exist elsewhere in the cosmos for life to emerge? Having examined planetary differentiation and internal structure, the next stage is to explore the atmospheres of each planet and how they influence habitability. Factors such as the greenhouse effect and magnetic field loss will be examined in detail, offering insights into the conditions necessary for survival and the potential for life beyond Earth. The closest world to the Sun in our solar system is Mercury. At first glance, it seems like a barren rock, but Mercury is one of the most complex and paradoxical worlds, holding geological secrets that challenge every assumption we make. Interestingly, Mercury lacks a thick atmosphere and a strong magnetic field to shield it from the Sun's relentless radiation. Unlike other planets, it has no substantial protective envelope to guard its surface from solar and cosmic impacts. The Sun beats down directly, driving daytime temperatures up to 430 degrees Celsius, while nighttime temperatures plunge below minus 180 degrees Celsius. These extreme temperature swings create a surface incapable of sustaining life. Yet they also give Mercury a uniquely dynamic and ever-changing landscape. What many people don't realize is that Mercury's surface is far from a static plane. Instead, it is etched with enormous wrinkles known as lobate scarp. These cliffs, some stretching hundreds of kilometers long and rising several kilometers high, were first glimpsed in detail by the Mariner 10 spacecraft and later confirmed with stunning clarity by NASA's Messenger mission, providing direct and spectacular evidence of a unique geological phenomenon. The source of these wrinkles lies deep beneath the crust, Mercury's massive iron core. Over billions of years, the core cooled and contracted. As it shrank, it exerted tremendous pressure on the surrounding crust, forcing it to crumple and fold. The result is a fractured and wrinkled surface, unlike Earth's plate tectonics or the volcanic resurfacing of Venus. This process reveals a distinct evolutionary path for a cooling world, while also showing that Mercury still retains immense residual energy from its past, making it a critical subject for studying rocky planet evolution. Perhaps the greatest paradox, and one of the most intriguing features of Mercury, is the presence of water ice at its poles, a discovery that seems to contradict the planet's image as a sun-scorched world. How could a planet with scorching daytime temperatures harbor frozen water? The answer lies in the universe's clever design, impact craters. At Mercury's poles, the planet's rotation axis is almost perpendicular to its orbital plane. This means sunlight never reaches the floor of certain deep craters. These permanently shadowed regions act as natural cold traps. While the surrounding surface burns under the sun, the crater floors remain below freezing, allowing ice to persist for billions of years. This is not just a hypothesis. Radar observations from Earth revealed unusually high radar reflections at Mercury's poles, consistent with the presence of ice. Later, the neutron spectrometer aboard Messenger confirmed this by detecting abundant hydrogen, an undeniable signature of water. This discovery not only transforms our understanding of Mercury, but also offers a vital lesson in the extraordinary adaptability of matter in the solar system's harshest environments. Mercury is not merely a planet of extremes. It is a world of geological and chemical mysteries waiting to be explored, demonstrating that even the harshest places can conceal the unexpected. With a size and mass comparable to Earth, Venus took a dramatically different evolutionary path. Its story is not just a geological tragedy. It's a stark warning about the fragility of planetary balance. Scientific evidence suggests that Venus may once have been a world with oceans and a temperate atmosphere. However, a catastrophic event unfolded, a runaway greenhouse effect. As solar energy heated the surface, the oceans evaporated, releasing massive amounts of water vapor, a potent greenhouse gas. This feedback loop accelerated uncontrollably. Higher temperatures caused more water to evaporate, which in turn drove temperatures even higher, creating a vicious cycle until all water vanished completely. The result of this catastrophe is a dense, suffocating atmosphere composed of over 96% carbon dioxide, cloaked by thick clouds of sulfuric acid that cover the entire surface. This atmosphere acts like a heavy blanket, trapping heat from the sun and generating surface pressure 92 times that of Earth. Venus's average surface temperature is hot enough to melt lead, making it the hottest planet in the solar system, even hotter than Mercury. One of the most puzzling mysteries revealed by missions like Magellan is that Venus's surface appears remarkably young, only 500 to 700 million years old, despite the planet itself being 4.5 billion years old. This suggests a terrifying possibility. A global resurfacing event erased all traces of its ancient geology. Instead of slowly moving tectonic plates releasing pressure gradually, Venus's crust seems to have accumulated heat and stress over time, then erupted in a single massive volcanic event, melting and renewing the entire surface. Evidence of this event lies in thousands of volcanoes and unique structures, such as pancake domes formed from highly viscous lava. Afterward, Venus' surface became eerily still, showing no signs of significant geological activity. Unlike Earth, Venus lacks tectonic plates, meaning it has no self-regulating mechanism like Earth's to moderate surface temperature, leaving heat to build unchecked. Adding to its peril, Venus lacks a strong magnetic field like Earth's, leaving it unprotected from solar wind, a factor likely responsible for the planet's extreme climate. The story of Venus is not just a planetary lesson. It's a cautionary tale about how easily a world can lose the conditions necessary for life. Unchecked greenhouse effects, atmospheric instability, and the absence of magnetic protection transformed Venus from a potentially habitable planet into a dead world. From this cautionary tale, scientists draw critical insights into Earth's climate change and the urgent need to safeguard our planet from runaway environmental transformations. After exploring Venus' deadly fate, the next question is, could Earth follow the same path? Can our planet avoid Venus' destiny, or are we standing on the edge of an uncontrollable climate crisis? Earth is a rare combination of geological factors that transformed an ordinary rocky planet into a world teeming with life. It was never a perfect model from the start, but rather the product of violent events and delicate balances. A natural experiment conducted by the cosmos, and we are fortunate to be its outcome. Looking at a map of the world, the continents seem to fit together like pieces of a puzzle. This is the hallmark of a unique geological mechanism in the solar system: plate tectonics. Unlike Venus with its rigid stagnant crust, or Mars with its completely cooled surface, Earth's crust is divided into roughly 15 large and small plates. These plates drift atop the semi-liquid mantle, continuously moving, colliding, sliding past one another, and subducting. The journey of these tectonic plates not only produces majestic mountain ranges, deep valleys, and powerful earthquakes, but also serves as a grand climate regulator, a natural air conditioning system for the planet. This process drives the carbon silicate cycle. Carbon dioxide in the atmosphere combines with rainwater to form carbonic acid, a weak acid strong enough to slowly erode silicate rocks on land. This chemical weathering releases calcium and bicarbonate ions, which rivers transport to the oceans. Marine organisms use them to build shells and skeletons. And when these organisms die, their remains settle on the ocean floor, sequestering carbon in sediments. These sediments, along with subducted tectonic plates, are gradually drawn deep into the Earth's interior. At pressures and temperatures hundreds of kilometers below the surface, the carbon-bearing minerals are converted back into carbon dioxide, which is then released into the atmosphere through volcanic eruptions. Earth's habitability also relies on a crucial trio of sustaining factors. First, long-lasting liquid water. Earth's Goldilocks distance from the Sun, known as the habitable zone, allows water to exist in all three states with significant quantities in liquid form. Water is not only a solvent for all biochemical reactions, but also plays a critical role in regulating global climate, thanks to its high heat capacity, which buffers temperature swings between day and night. Second, a strong magnetic field. Generated by Earth's liquid iron core and rotational motion, the magnetic field acts as an invisible shield, protecting the atmosphere from solar wind, the electrically charged particles streaming from the Sun. This process, known as the geodynamo, arises from convective currents in the molten outer core that generate a powerful magnetic field. The Earth's liquid outer core, filled with molten iron, circulates convectively to generate electric currents, producing a strong magnetic field. Without this shield, solar wind would gradually strip away the atmosphere, just as it did on Mars. A planet without an atmosphere loses both its greenhouse effect and its ability to retain liquid water on the surface. And finally, the carbon-silicate cycle. Together, these three elements create a stable, long-lasting biospheric window. Without any one of these components, Earth might have met the same fate as its neighboring planets. To fully appreciate Earth's fortune, we must consider a pivotal early event, the giant impact hypothesis. Around 4.5 billion years ago, a Mars-sized body named Theia collided with the early Earth. The impact produced massive debris that eventually coalesced into the Moon. The Moon is not merely a companion, it plays an essential geological and climatic role, stabilizing Earth's axial tilt. Earth's rotation is tilted about 23.5 degrees. This tilt creates the seasons. But more importantly, the Moon's strong gravitational pull has kept this tilt nearly constant for billions of years. Without the Moon, Earth's axial tilt would fluctuate wildly, triggering extreme and chaotic climate swings. From sudden ice ages to intense melting periods, making the development and persistence of life nearly impossible. Earth's story illustrates that life is not guaranteed. It is the extraordinary result of a series of fortunate events and rare geological processes. It also serves as a reminder that our world balances on a delicate line. But what happened to Mars, the planet that once seemed capable of supporting life, only to become a cold, dead world? Mars wasn't always the cold, barren world we see today. It was once a place brimming with promise, a planet capable of sustaining life. Over decades of exploration, a great secret has been revealed. Mars used to be warmer and much wetter. rovers like Curiosity and Perseverance, acting as robotic explorers, traversed the red planet's surface and sent back undeniable evidence. They discovered traces of dried riverbeds and valleys carved by ancient waters, channels sculpted by rivers that once flowed freely. Notably, at the Jezero crater, Perseverance is investigating what appears to be the remnants of an ancient lake bed and delta plain, where water once poured in and deposited sediments. The presence of clay layers and stratified deposits indicates these bodies of water weren't fleeting. They may have persisted for millions of years. Even more compelling, scientists have found minerals that only form in the presence of liquid water, such as clays and hydrated sulfates. These chemical signatures confirm that Mars once harbored a stable aqueous environment. The data paints a vivid picture: a planet with a thicker atmosphere, a vast northern ocean and raging rivers. A world where life could have flourished. But what happened next? Why did such a promising planet devolve into the cold, desolate desert we see today? The answer lies in one crucial difference between Mars and Earth: the loss of its magnetic field. Billions of years ago, Mars had a molten core and its own magnetic field, generated by a mechanism similar to Earth's geodynamic. However, because Mars is much smaller than Earth, it cooled far faster. This cooling shut down the core's activity, and the planet's magnetic field gradually disappeared, leaving Mars exposed to the ravages of space. Without a protective magnetic shield, Mars' atmosphere became vulnerable to the relentless stream of charged particles from the Sun, solar wind. Measurements from NASA's MAVEN probe confirm that this process continues, showing Mars' atmosphere being eroded bit by bit every second. As the atmosphere thinned, a chain reaction unfolded. Air pressure dropped drastically, making liquid water on the surface impossible to sustain. Water either quickly evaporated or froze permanently as ice at the poles and underground. Without a greenhouse effect, global temperatures plummeted, transforming the planet from a warm, wet world into the icy, dusty desert we observe today. Mars stands as a sobering reminder of how a planet can lose its ability to support life due to a seemingly small internal change: the cooling of its core. Life on a planet doesn't rely solely on distance from its star. It depends on a delicate balance of geological and physical factors. It is a valuable lesson on the importance of a magnetic shield and a stable atmosphere. The tragic tales of Mars and the catastrophic saga of Venus are profound lessons. grand natural experiments that the universe has set before us, helping us better understand ourselves and the future of Earth. From a planetary science perspective, we are not only exploring distant worlds, but also re-examining our place within a much larger cosmic picture. The stories of Venus and Mars represent two extremes in a lesson about climate. Venus teaches us about the disaster of a runaway greenhouse effect, where a dense atmosphere and immense carbon dioxide transformed it into a furnace-like inferno. In contrast, Mars demonstrates the tragic fate of a planet that lost its atmosphere and greenhouse effect, becoming a cold, barren world. Juxtaposing these narratives, we recognize the fragility of Earth. The climate fluctuations we face today are not merely environmental, they are physical and geological challenges. Understanding Earth's carbon silicate cycle, a complex regulatory system that has kept our planet stable for billions of years, has never been more crucial. We are, perhaps unwittingly, interfering with a system that has existed for eons. And what befell Venus and Mars serves as the clearest warning. From the scars on Mercury and Mars, we know that collisions with objects in space pose a real threat. These lessons are not just history, they are a map for our future. The journey across the Tellurian worlds is not merely an exploratory voyage, it is a profound lesson in understanding the seemingly monotonous rocky planets. From a single disk of dust and gas, each world has solved a complex puzzle of heat, water, atmosphere, and magnetic fields, charting entirely divergent paths of evolution. Mercury is a world shrunk and scarred, Venus a tragedy of runaway greenhouse devastation, Mars a paradise long forgotten. And Earth, with its tectonic scars and strong magnetic field, is an extraordinary stroke of luck, a miraculous outcome of a perfectly orchestrated chain of geological and cosmic events. They are invaluable tools that allow us to reassess our place in the cosmos and confront current challenges. By understanding the catastrophe of Venus, we gain a stark, profound awareness of Earth's climatic fragility. By examining the fate of Mars, we comprehend the critical importance of a protective magnetic field and how easily an atmosphere can be stripped away. Planetary science equips us not just to reflect on the past, but to anticipate the future. Projects like the Rubin Observatory are more than scientific endeavors. They are integral to a planetary defense framework, helping map risks and prepare for what lies ahead. As we dream of setting foot on Mars or extracting resources from asteroids, science offers the roadmap to navigate the universe wisely and responsibly. In a universe rife with turbulence and grand-scale catastrophes, Earth is not just an invaluable legacy, it is a rare sanctuary shaped by both the relentless laws of physics and the subtle miracles of balance. Protecting this legacy is not merely our responsibility. It is a quiet tribute to the countless forces and events that converge to make life possible.
This young world is alive. Volcanic outgassing releases the crucial elements needed for an atmosphere.
Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.